All right, let's start. So, hello again. I'm Flavius Dinu, a developer relations manager here at Lens. And in today's webinar, I will talk about deploying AI agents without exposing your data. The premise here is actually simple. Everyone wants to put agents on real systems, but the moment an agent actually touches production environments, security and legal teams start asking hard questions. We will explore why AI agents break your security model, what are Lens agents and LNS. We're going inside the architecture and you're going to see how we do isolation, how we handle credentials and data as well. We'll walk through our audit trails, integrations, and deployment options, and then we will have a demo in the Q&A. Let's start with the shift. So old school security kept threats out actually, but agents are different and they flip that because they run inside your perimeter, usually on humans' implied credentials. And there are four important things right here. So an agent isn't actually a person and it isn't a service account. An agent reasons, it chains actions together, and actually decides at runtime which tools to call with elevated privileges. And non-human identities right now, they already outnumber humans around 45 to 1, and this is up to 144 to 1 in cloud-native environments. And these stats are actually from the Cloud Security Alliance report. The thing is, you can actually spin up thousands of non-human identities in the time it takes you to onboard a single employee. And the credentials are actually the crown jewels here, because if you add a secret to an agent, it becomes a walking secret store. These secrets are leaked through logs, they are leaked through dependencies, model output, and other methods as well. And the quarterly access review is actually meaningless, right, against a bad decision that's made at machine speed. Yeah, an overprivileged agent can actually exfiltrate data at machine speed without ever compromising human credentials. It doesn't need to phish anyone. It's already inside. It's already trusted, and it moves faster than any human attacker. That's the threat model we designed against. So what do you actually have to do about it in practice? So there are a couple of things that you could do to secure non-human identities. You should ensure that credentials are supplied at a control layer at the runtime. If you add them in the agent code, if you add it in the files or the model context, you are just inviting an attacker to compromise your system. You should also try to scope by least privilege. So allow list only what's needed, deny everything else if possible. Also binding the identity as well, so every action is actually traceable to a principal. Audit everything, including the request you actually denied. Cap the blast radius with spending limits, and actually rate controls as well, and read-only defaults. And it's also very important to actually define autonomy explicitly, and you should match human oversight to risk. So observe, advise, and act on what the agents are actually, telling you. So, all right, if you don't know what Lens Agents is from our previous webinar, it's the governed platform for running AI agents on enterprise systems. And you can actually install it pretty easily by using Helm into your own Kubernetes clusters. And this is not a SaaS that we actually operate on your behalf. It runs in your infrastructure. We have four pillars here: governed sandboxes, policy control access, credential isolation, and also audit trails. And it governs three kinds of agents in a single way, basically, in the same way, actually. So we have desktop tools like Cloud Code or Codex, external autonomous agents that run in any framework, and agents that are actually built directly on the platform as well. So now LNS, this is a new one. So LNS is actually the open local runtime for agentic workloads. It's a local microVM sandbox for your laptop, and this will actually be open sourced and Apache 2 licensed. It's the sandbox you'll actually leave running on your local machines, and it uses the same core policy, credentials, and audit model as Lens agents, but it does that locally. So it uses connectors instead of paste-to-draw secrets, and the policy you write are actually yours. And the story is this: you develop locally in LNS, then scale to the organization with Lens agents by using the same artifacts, the same policies, and the same experience. So right now, our Lens organization has three different products. So Lens is the Kubernetes IDE 1 million plus engineers already use. LNS is actually the local runtime for individual developers and agent builders. And Lens Agents is the organization scale platform for security, platform, and IT teams as well. And if you look at the bottom row on this slide, everything runs in your environment, your desktop, your machine, your infrastructure. Nothing here is a hosted black box. And I guess that's the important part, especially when it comes to your data per se. So yeah, here is the problem that you need to solve. You need to contain the blast radius, especially if you have an agent that's powerful enough to be useful. You have to actually bound it to what it can reach and what it can do. And let's look at exactly how you can actually do that. So basically, your agents should be deployed in a sandbox, and they are, if you do that with Lens agents, they are isolated in 7 ways. So the agent will run as an unprivileged user. It has no path back to root. The kernel actually rejects all egress except loop back and establish connections using IP tables. Every outbound call is actually forced through a forward proxy with a default deny allow list. The file system is ephemeral and it's wiped on recycle. We have idle sandboxes that shut down to shrink the exposure window. And there is a deliberate privilege split. So the proxy holds privileges, the agent never does in our case. And in production, Kara containers or a gvisor runtime class basically adds per-sandbox microVM isolation. So even a fully compromised agent will stay in the box. It cannot do anything. And now when it comes to credentials, they are injected and never embedded. So secrets are applied actually at the network boundary. They never touch the agent's code. They never touch the agent's files. They never touch its prompts or logs or even memory. We have a per-sandbox in memory ephemeral CA that lets the proxy terminate the agent's TLS, swap in the real credentials, and then this one dies with the sandbox per se. The agents, so the AI agents that you're using are going to actually hold fake credentials, and the real STS credentials are actually signed in at the boundary. For Kubernetes, for example, because you know us from Kubernetes, right? We have a tight integration with Kubernetes. It's like a 60-second auto-rotated token through the proxy. There is no kubeconfig token that lands on the disk. Credentials are actually scoped to method and path, so reads cannot become writes, for example. And stored credentials are encrypted, and the agent tokens are never stored at all, only their hashes. So the punchline here is actually this. If you compromise an agent, you're going to walk away just with placeholder strings. You won't get access to absolutely anything. Now, credentials are actually just one half of the story. The data, so basically the data the agent retrieves still flows to the model as context. So we have to actually do something about that as well, right? So what we do is we actually classify it before inference. So this is enforced actually at the model boundary. Every request and response passes through the proxy, so it can inspect all of it. And detection is 2 ways. Basically, we have a fast regex for structured PII, and we also have an optional NER model for names, addresses, and free text as well. Detected values are masked with placeholders before the model ever sees them. Then they are actually rehydrated in the response for the agent. And it's actually failed closed by default. So if detection errors, the request is blocked and it's not actually forwarded. Here comes another problem, and this one is actually a practical one. None of this matters, right? You can have the best governance in the world, but if it doesn't run with the systems you already work with, it's not going to work for you. It has to actually fit your enterprise. So let's look at how this connects together and where it actually runs. So basically, we have deep integrations for Kubernetes, for AWS, for GitHub, for Slack, each with their own agent identity, role-based access control, and also credentials applied at the boundary. We have a policy-controlled proxy that reaches any HTTP or HTTPS system by allow list. So you can easily connect to Jira, for example, Salesforce, ServiceNow, Backstage, internal APIs, whatever you need. We also have an MCP server registry, so you can bring it in upstream. You can bring in actually upstream MCP tools. and have them actually discovered and governed by the policies that you define. And we also have batteries included. So every sandbox that we give you ships with kubectl, AWS, GH, Git, JQ, Cloud Code, and other things as well. So when it comes to the platform per se, to the Lens Agents platform, you can actually deploy it anywhere you want. You can deploy it in the cloud. You can have a hybrid deployment. You can have an air-gapped environment. You just use Helm to deploy it in your Kubernetes cluster. It doesn't matter if it's AWS, Azure, or GCP. And clusters connect basically over an outbound tunnel. They have no inbound ports. It's firewall friendly, basically. And inference can be any provider, AWS Bedrock, for example, or fully self-hosted models for the air-gapped use case. And again, the bottom row is the whole point that actually matters, because your data stays with you. You get the same policies, identity, credentials, and audit everywhere, but the data stays with you. It's not with the model provider. When something goes wrong, or when someone simply asks what happened, you need to be able to answer who did what, and that's audit. And yeah, we have, of course, an audit trail. It's a complete one. It works across 7 surfaces, as you can see on the left-hand side on the slide, with MCP, Kubernetes, Shell, forward proxy, and all the other things that you see there. And every event in our audit trail actually carries an actor, an action, a resource, a result, and a timestamp. You can query by agent, you can query by time range, you can query by action or resource, export the data to your SIEM platform. So the question from the intro, which agent touched which data, with whose access, and when did it actually touch that data, finally has an answer. So yeah, enough with the slides, I guess. Let me show you this working in practice. So we have a setup. We have a sandbox set up. It's connected to Slack. It's connected to a Minikube cluster, a GitHub manifest repository, and it's actually running a Kubernetes triage skill. Basically, what I'm doing here is I have an Argo CD that runs an apps pattern from Git. We break a manifest, Prometheus fires, and the alert lands in Slack in the end. After that, I just ask it to open a pull request with a fix. I'll merge it. Argo CD will automatically heal the cluster, and I'll ask the agent to confirm that everything is okay. So yeah, without further ado, I'm going to play the demo. So here's a message that my AI agent wrote to Slack after it noticed a pod in my Kubernetes cluster failed, investigated it on its own, and then even wrote up the root cause with its confidence level as well. In the next couple of minutes, I'm going to let that agent triage a real failure, propose a fix as a pull request, and watch my cluster heal after I merge it. And the whole time it never had access to my credentials, and it never had the power to touch my cluster directly. So this is my cluster. It's a local Minikube cluster. I've already connected it to Lens, the Kubernetes IDE that has over 1 million users worldwide. And there's nothing exotic here. I just have a couple of workloads that run in this Minikube cluster, but they would run in the same way in AWS EKS, AKS, or even in GKE. So it doesn't matter where these workloads are. The story would be the same everywhere. So in this cluster, I have Argo CD already installed, and what I can do is I can port forward to it and just access it. And as you can see, I have a couple of applications in here. I'm using an app of apps pattern to deploy them. There is one root application that spawns a child application per workload, and every one of them is actually defined in a Git repository. So Git is the source of truth. If it isn't in this repository, it shouldn't be in my cluster, and the way you change the cluster is actually just changing this repository per se. And let's remember that, because it's the key to how the agent stays safe. The agent can read the cluster, but the only way anything actually changes in the cluster per se is a commit that a human has to approve. So now I'm in the Lens Agents platform, and I actually have a project right here called Default. I'm already connected to my Minikube cluster, as you can see right here, and you can see it had some activity in the last 14 days. I have a couple of credentials defined, so I have my GitHub personal access token and the Slack app token and bot token in order to ensure that my agent can communicate with Slack and with GitHub. The important part you need to understand is these credentials are not in the agent, they're not in its code or its environment, its prompt or its memory. They live at the platform boundary, and when the agent actually makes a call to GitHub, for example, the platform injects the real credentials on the way out. The agent just sees the request succeeded, and if the sandbox were actually fully compromised, an attacker would walk away just with placeholder strings. Now, if you go to policies, for example, we can see that we have a default policy that has the integration to the Minikube cluster. And in here, we have defined what domains all the agents that have this policy attached can access per se, all the credentials they have access to, the environment variables, connectors. And we can also check if we can enable or disable PII masking. So let's actually enable it. I'll just go to edit, and we have here the option for PII masking. I'll just click on the button right here, and you can see a lot of things that you can actually mask per se. So let's click on save as well, just to have this enabled. And we can see also that this policy is bounded to everyone, so every one of my agents will have this policy automatically attached. So if I go to sandboxes, you can see here that I have two agents. One is for AWS and the other one is for the Minikube cluster per se that I showed you in the beginning of the demo. So let me go to this one. So this is the agent per se. It's trained through conversation. So if you go to chat, we're going to see my latest chat with it right here. If I do skills, you're going to see the available skills this agent has access to. And this is a skill you saw in the beginning in Slack. So this is the Kubernetes event triage. It reacts to Kubernetes warnings and errors in real time. So let's give it a go and see how this would look like. So before jumping into the Argo CD example, let's do something that's simple. So in Lens, what I'll do is I'll actually open Cloud Code. And when I do it, this will automatically load my Minikube context into it. And what I'll do here is I'll actually ask it to create a pod that doesn't work. And I'm doing that because I want my bot to actually capture this event and then post it to Slack automatically. So let's say create a pod that has an error. And what it does right here, it's creating an Nginx pod with an image tag that doesn't exist. So let's apply it. And we can see here the broken pod, and in a couple of seconds, we will get notified on Slack as well. And as soon as I made that pod with the error, you can see in the schedule task of your agent that the KTS event triage task was scheduled. And now we can see that the schedule task has actually arrived in Slack. We can see exactly what's failing. We can see the severity, the root cause with a high confidence as well. And there is also a suggested fix for it, just to run this command and you'll be good to go basically. Now let's go for something real in our GitOps workflow, and I'm going to actually play the part of a well-meaning engineer that has a bad afternoon. I'll bump an image tag in the repo, except that tag won't exist, and this is exactly the kind of change that actually sails through and then quietly breaks your cluster. So in my repository, I'll go to my manifest and then to my deployment, and I'll make a change here. And we can see that we have the image Nginx stable Alpine. I'll just add another E here, commit the changes with a new branch, of course, and propose the changes, create the pull request, and in the end, I'll just merge it and wait for Argo CD to sync it. And of course, delete the branch as well. So now I'm back in Argo, so let's wait for this change to actually sync. We can see now the status is progressing, so let's take a look, and we can see that we actually have a broken pod right now. Our agent will actually pick it up on its own and start investigating with read-only kubectl. So we can see the triage results have arrived in Slack. We can see that we have an issue with our Nginx pod. It's stuck in an image pull back off. It tells us where this happened, the severity, the root cause again, what's the evidence and the suggested action. And it tells us that this deployment carries an app Lens Agents Nginx demo, and you run Argo CD, and this may be Argo managed. So let's talk to the agent. So let's say, yes, this is managed by Argo CD. The manifest is in this repo that you should already have access to. Please fix the issue and open a PR with the fix for me. So we can see the PR is up. If we merge it, Argo CD will automatically resolve it. So let's see the PR. And we can see that it has a message in here which tells you the problem, the fix, and we can see the files changed, and we can see it fixed the image from Alpine with double E to Alpine. So this is ready to merge, so let's merge it. And now let's go to Argo CD and see the sync. So we can see the sync is okay. We can see the comment, it merged the pull request, and it's fixing the correct Nginx image tag typo from stable alpine with double E to stable alpine. This is basically having an agent operating exactly like a good junior SRE. It did the work and it's handing me a reviewable change instead of poking production. And now to close the loop, I'll actually ask the agent to check its work. So check if everything is okay now with this particular pod. And we can see that everything is healthy. The PR was merged and Argo CD is synced. And basically you have everything in a single workflow. You detect, you triage, you propose, you approve, you verify. A full incident is actually handled with a human in exactly one place, the merge button. And now if you go back to Lens Agents and select Audit Trail, we can see all the events that have happened. We can see where they happened. So we have events in Slack as well. We have events in our Kubernetes cluster. We have events in the platform. We can see their results. We can actually, just filter them by their source. We can filter them by results and by actors as well. If your security or legal teams ever ask you which agent touched what, when, and with whose access, that question actually has an answer right now. So you can actually use it in any Kubernetes cluster, and this is pretty well documented, but what you can actually do is just feed that document to Cloud Code to do it for you. So here is the doc. It explains what you have to do in order to run Lens Agents locally, so I'll just copy it, go to a terminal and just start Claude. And I'll say, please install Lens Agents in my Kubernetes cluster. It will verify some prerequisites initially. And now you can see it actually runs the helm install command to actually install Lens Agents. And it will actually expose the platform with a port forward. And now I can access it. And we are asked to actually activate Lens Agents right now. So we can click activate and you will see a verification code. And now we're asked to grant access to Lens Agents and say yes. And we can now close the browser window and go back. And we are actually getting redirected to the Lens Agents platform. We have to create an organization. Let's do a default one. Click on it. Now go to new project. Let's say default. And here we can actually create sandboxes, policies, credentials, integrations to AWS, Kubernetes, and everything else that you can actually do with Lens Agents. We also have an MCP server for Lens Agents, so let's say MCP is this one, Lens HQ, and we can view all the tools. And as you can see, you can list orgs, create orgs, update them, and do 173 different things like create sandboxes, create MCP servers, delete them, create connectors, get user usage credentials, and so on and so forth. So we saw a governed agent doing real work. It caught the failure, explained it, proposed the fix, and verified the recovery without ever holding my credentials and without the power to touch my cluster on its own. We also saw that we can install Lens Agents locally and that we also have an MCP server available. And as mentioned before, LNS, our free open source local microVM sandbox for Mac, Linux, and WSL will be available soon, and it will help you actually run AI agents, coding assistants, autonomous agents, custom agents, commands, OCI images, containers, scripts, and much more. Okay, cool. So that was the demo actually. So yeah, let's recap. So agents are actually non-human identities, so you should actually govern them like that. You need to inject credentials, isolate the runtime, classify the data, and actually audit everything. LNS is free to run. I mean, it will be free to run because it's not yet released, but it will be free to run on your machine. It will be soon open sourced. And the Lens Agents platform can be actually installed pretty easily with Helm in your own environment. There is one more very important thing that's pretty timely. The EU AI Act's obligations begin applying in August 2026, so less than a month from now. And the audit trail and the autonomy controls in Lens Agents actually map directly to its transparency requirements. So I wanted to actually thank you for attending this webinar. If you are interested in booking a demo to see even more about what we can do in the AI zone for you, reach out to our general manager, Kyle, at lenshq.io. If you have any other questions, feel free to connect with me on LinkedIn, X, or any other platform you see fit and just ask. Thank you for attending one more time, and I'll see you in the next one.